Welcome to lesson 5. Now, today is going to be a very fun lesson because we're basically, it's going to be deploying fastai along with a workshop of what that's like. So I don't have it prepared. I have, obviously some of it prepared, but I don't really have it prepared. We're going to build a Gradio app live from these fastai models we're going to build. Now, the first part for today's lesson is I'm going to be talking a little bit about the tail end of lesson 4 yesterday. Because if you remember, we talked about freezing the model and layer groups and splitting. And there were a few questions on that. And when it comes to fastai, a very important concept, because it's the whole idea behind this transfer learning, freezing layer groups, and basically having the model do well in terms of fine tuning. And so today we're going to start with just a brief revisit of it. So all I have here is a scratch pad. I'll release this notebook later. Basically, we have two models, right? So I have this regression model that does essentially y equals mx plus b, right? That's all this is doing here. And it has two parameters. And here we're storing these layers as attributes. Now I'm going to see if this parameter method works. If it doesn't, we'll go back to a linear model and try making that simplified. But for now, hopefully this will work. And then down here, I have the equivalent done as a module stored in self.linears that we can index into. And based on these, we're going to, together, try and freeze the regression model's A parameter and keeping B unfrozen using a custom split function. Now, if we remember, basically with splitting functions, how they work is it needs to be a method that returns essentially a list of layer groups or parameter groups. And that's all it is. And this list needs to map to whatever layers you have. Now it uses a fastai method called params. Basically, it's this function in Torch Core that returns all of the parameters of M, with M being some model. So say we do regression model and say A is 1, B is 2, right? So if we do net equals, and then if we do params of net, it should show 2, I want to say. Yeah, so it's a list of all of the parameters for this entire model, right? So here we have the parameter of A and the parameter of B. And the way fastai does this is it uses a recursive method on all of the parameters inside of the model itself. So it doesn't actually matter how it's defined. What do I mean? Let's do the same thing with this module list instead, right? So if we say net equals my module, 1, 2. How did I mess this up? Float tensor is not. Oh, that's why, because it needs to not be a float. And actually, these might need to be layers themselves, which is fine. We can change these to an end linear 1, 2. Well, it actually needs to, these need to be layers themselves for module list. So we'll go something like this and then return. Really, this should be, I had the documentation up for module list. Yeah. So we can do for I, L and enumerate self.linears. We'll just steal from the documentation itself. X equals self.linears at, yeah, I guess we could do this. We could just steal it 1 for 1. And then return X. And this should be, X equals. So basically it just takes a list of layers that we actually wanted to run through and performs some sort of iteration over that declaration that we had, right? Self.linears. What's important here is just the fact that we're using a module list, as this is what the question was. So now if we run params again, you'll see that we have these parameters again, right? And these are a little different than before because these are now the weights and biases for a linear layer specifically. So it's a little different. But you can see that it has all of these here. And so now if we wanted to do, say, a splitting function, right? We just need to have it be able to map through and index these parameters, essentially. But basically, we can do something like net linears at 0, net.linears at 1, .map params, right? So this is essentially aligning to the splitter that we wrote last class, and instead just using the module list defined by the attribute, which we can index into to get the layers. And as long as we can get the layers that it needs and pass in all of them at some point throughout this, we can generate this sort of parameter mapping as a splitter function, pass it into the learner, and we're on our way. Hopefully this makes a bit of sense. I will probably write up the snippet and just share this notebook directly. That's basically sort of more on the splitter and how that really works. It's all done through this sort of params that you see here. That's why we do that L map, well, you saw it a moment ago. This sort of L map params things when we create our splitting function, because what fastai cares about is I just need a list of whatever layers need to exist in A versus B. And so at the end of the day, that's all this is. Let's get talking about probably my favorite lesson we're going to have of this entire course, deployment, and specifically inference. Well, that's sort of oxymoron. Both inference and deployment. Now, what we're going to walk through is deploying with fastai, and then I'll briefly show what deploying without fastai looks like. We'll sort of take what the code base has been presented there with these two different ideologies, right? Keep fastai versus remove fastai. And we'll deploy them in a Gradio app reflecting this. So there'll be two Gradio apps that I'll show. You'll find that the interfaces for them both are actually quite similar, and just show what it takes both dependency-wise and requirement-wise to deploy with Gradio, and in turn then take that and migrate it to like a Hugging Face space, for instance. Now, the reason why this is being included, because you notice there's a little tidbit that it includes some of running with fastai, and originally this wasn't even going to be part of this course. But when I was thinking about what did I want new people taking the course to get from it, what is truly important, and what do people that take fastai not know how to do very well. Deployment is the number 2, but it's the number 2 most important thing. However, there's only 2 things that are flawed, and running will take care of the rest. That's software engineering skills. But when it comes to just raw doing fastai, this is number 1. And the reason for that is fastai, as I sort of told you and showed you throughout this course, has inference hardware in it, right? We saw get preds, we saw predict, but when you want to deal with options like dependencies, code maintainability, and more, code reliability, how long that code can survive, these are very important concepts and ideas to learn about for fastai specifically, because fastai is not stable in the sense of 2 years down the road, the code will work if you set up everything the same. It's not dependable in the sense of it's got a lot of magic going on, and if you want to customize your inference pipeline to do certain things, the code is going to look very strange unless you know fastai. And so what we're going to do here is basically show these 2 different methodologies. The first is shown for posterity. So if you want to do something quickly where it doesn't matter what the code looks like, you don't care about posterity or just, making sure it'll work 2 years down the line just to get something going as a quick demo. That's what this first part of this lesson is going to show you. And it's going to be things we've already looked at. Both of these are things we've already looked at, just not quite in depth. And then the second one is removing fastai, which when I say we've looked at this, we've looked at it from a data perspective, but we've never quite looked at it from a modeling perspective, right? Because fastai creates these models in these various ways, and they have sometimes custom layers they need to use. And so the model itself also acts as a dependency on fastai. Another way to put that is, In order to load the model into memory, fastai must exist in the ecosystem. And so we're going to show what that looks like to remove the magic head that we made in the last lesson and fastai's general magic head and deploying them. Now, because we're going to focus on that, I just have some very quick boilerplate code here using our favorite example, pets. Create a very quick model here. We don't care about metrics or anything. We just care about having something that marginally works okay. The important part here is get a trained model, which if you're following along at home, ideally for this lesson specifically, have a trained model you're ready to deploy. Because this part is going to be talking, and then I'm going to pull up VS Code and do all of this right in front of you. Now let's talk about learn.save versus learn.export. This is one of the most common areas I've seen users get confused with the library as far as what it does, how it works, and what should you use. And they're both a bit different. So save and export both will save the model weights and save the optimizer weight and optimizer states. Both of them will not save the data. So when you do learn.export, the original data loaders are removed and stripped of all of their data. What you save instead is those transform pipelines we made earlier. And so those pipelines are what's loaded in, and so it knows how to load the data and prepare the data so you can make those test data loaders. And that's why only export actually saves that. And so another way to think about that is you should use save when you don't plan on doing inference with fastai, for instance, or you just want to do, say, like checkpointing of a model's weight. Then you would save via save, so you can have the model weights and optionally the optimizer state. Whereas export is strictly there for, do I need to know the state of the transforms of my learner? Which, there could be options where you want to do that with intermittent training and checkpointing. You might want to have access to the data loaders that you load in. And so basically, this is what determines which part of the API you want to use. For this lesson, we're going to use both. So the first part, when deploying with fastai, we're going to use learn.export. And then the second part, where we're not, we're going to use learn.save. The question of when or why do I need the optimizer state? If you're continuing training, you need to have the optimizer state as well so you can load in that exact moment. Because it's the difference between, say, I'm taking a frozen model and training it and saving those weights, right? And then I'm loading it in later to train unfrozen in a new setup environment. Like, that's my pre-trained model. And it's basically the equivalent of, say, the image net weights for us. I don't need the optimizer state for that because I just care about loading the weights and using a new optimizer. But the optimizer state matters if, say, I'm doing what we did in the last lesson, where I'm training a segmentation model for 5 epochs, saving it, and then say something horrible happens like CUDA out of memory, I want to be able to recreate the optimizer to the state where that crashed or where we'd be continuing. And so that's sort of the difference of when you need this specific information. For another perspective of that, by default, learn.save uses the optimizer state as well. And so does learn.load. Yep, exactly. Perfect. All right, looks like we're all pretty much good to go. Fantastic. Now let's talk about inference. And as I mentioned earlier, inference in fastai uses 2 different methods, predict and getPreds. Predict only uses a single image. That is exactly what it is solely defined to do. And then getPreds is designed to be multiple inputs. A real world scenario where you're scaled up to oblivion, you're going to be using getPreds. You're going to be doing batch-wise inference. And you're not going to be doing predict instead. And so what the rest of this lesson is going to show is predict versus getPreds and sort of recreating them one-to-one and some pitfalls that can happen from it. So first thing we'll do is, since we're using a fastai model and a fastai learner that we exported for this first part, to load it in, you're going to use learn equals load learner, which, in hopefully not trying to say learn too much, loads in a saved learner that's been exported. Now, when it comes to using predict, it's very easy to use and provides very readable outputs because it will automatically take your predictions and convert them into the class name. The disadvantages with this is, especially this first point, it is very, very easy to load in a learner and not have it actually use your GPU. That is the most common bug I've seen where people complain about fastai being slow. Even I did that when I was using fastai for a while, and I was like, why is load learner so much slower? Because by default, it loads it on the CPU, even if you have a GPU available. Because at least at the time, it wasn't common to have easy to access GPUs that you deploy on. Whereas now, with stable diffusion and whatnot, GPU deployment is much more common. And with predict, you can only do a singular input ever. So it is always a batch size of 1. So it's convenience at a limitation. Now, with predict, as we saw before, it operates by basically passing a file name or input. Now, this is important in the format of how the training or validation data is done. So that doesn't mean anything that can use pilimage.create. What it means is how our getters got the data. And so that's a bit different. So like say, for example, we were trying to do inference when we have our original model was trained on a data frame, right? So the type transforms are call reader, and it say gets the input from column 0. When we do predict, it expects that to be in the same format. It expects the way to do predictions is to pass in a data frame to predict, or a row, quite literally, a single row where the first column has the file name. That's the main frustration that this talks about here. And then the other parts are accidentally doing pre-processing that fastai does for you. For example, one thing I found very common is when people would predict using, say, byte data from website input, they would process the bytes before passing it to predict. And fastai would say, this is unsupported. What you're trying to do? Why are you trying to do that? Because fastai does that pre-processing for you. Even though it's not necessarily explicit, that's how that works. So those are two very common areas where this is an issue, basically. And the thing with the getX here is it's a limitation when you're doing things like call reader. It's not a limitation when you're doing things like byte data on predict versus, say, getting an image. Because that getX is get image files. It's not very explicit in what it does. It just returns basically the same thing, roughly, and it can actually use that. So let's, for instance, show a very quick example of predict. And I understand a lot of this is going to be review, but it's basically a lesson solely talking about that versus having it trickled, which for some of you, that I understand if you sort of fade out for a little bit, but for the rest of you, this is why we're making sure that you fully understand this. So we're going to get a single file name path, pass it to predict, and it got us the class name, the index of that class. So this is the 4th class in our vocabulary, and the decoded or argmaxed probabilities for that class. And as you mentioned before, Bombay comes from learn.dls.vocab. There was a decoding method for the loss function that's being used here that both gave us this option as well as this option. There's a little note here where you can't 100% rely on learn.dls.vocab, specifically because language models and language model training in fastai saves that in vocab. And so the safer way to do it would be doing learn.dls.categorize.vocab or learn.dls.multicategorize.vocab, depending on your problem. And you could use that as, do learn.dls.categorize. That could be getAtra with checking categorize or multi-categorize with different defaults. There's a few ways you can wrap around this to have it work and get that proper vocab for your class names easily. Now, the second one is getPreds. And if we take predict to be an option for batches of 1, getPreds is an option for any number of batches of any size. In terms of how it basically works, predict wraps around getPreds with a few other parts to get it to do what it needs to do. And when you use getPreds in the real world, your cycle is essentially create a test data loader, use getPreds, and then perform some post-processing to make them human readable. This is sort of what the diagram looks like. And a test data loader is basically a data loader that uses the validation transforms when sending data through the pipeline. And it has a note here in deployment, we utilize the test data loaders for preprocessing. Now, to create a test data loader, it needs a list of items that you want to do inference on. Or another way to put this is, again, similar to the input that is expected for basically building a data loaders. So this can't be a single row of data. It should be a data frame if we had a call reader and we're using a data frame. So to recreate predict, we can pass in a list of 1 to create our test data loader. And then we can use getPreds and pass in our new data loader to generate outputs. Now it'll return a tuple of a variety of things. The most important part for us here is this first one is the actual predictions, which is what we care about. And now to convert it back into what getPreds does, we can softmax, argmax, and decode the labels. And now we have Bombay 3 and these predictions. Now let's talk about a few pitfalls. The first one I mentioned is accidentally using predict. And this is even the case with getPreds. So you see here, all I did was load in the learner, right? I did not do anything else. We are using its defaults. So if we time this, there's a time magic that's hidden here, a time it. You'll see that using testdl on a single file name takes a little over half a second to do. And then on top of that, when we use predict, it's a tenth of that time, but still kind of slow. There's a few reasons for this. One of which is the learner was set to CPU. And let me see if we, yep. The learner was set to CPU. So that's the first issue with this. So we can change that by calling learn.dls.cuda. And now our getPreds here went from 723 milliseconds to 649. So it improved it a little bit, but that's still well over half a second. And the reason is due to also the fastai data loaders. By default, it uses multiprocessing to efficiently handle applying the item transforms and getting the data. And this is different than GPU processing, for the record. This is spinning multiple processes to apply things and getting it back individually. And so the solution to this is to say, okay, the number of processes I'm going to have is 1. There are no other workers that are going to be used except for the current. And now we can see that without having to deal with all this multiprocessing stuff, we bring it down from 0.6 seconds to less than a tenth of a millisecond, all because of this one value when you're using testdl. Now, when you use predict, it will automatically do this for that new data loader, which is why predict would not show the slowdown, and that's why this wasn't really shown here when we did CUDA, because otherwise this predict would look very similar to this. But with predict specifically, the part that we care about is load learner and passing in CPU equals false, because by default it is true, and as a result it will load it on the CPU. So the takeaway here is, there's ways to mitigate through these very common pitfalls of not using predict efficiently. And, there's going to be some frustrations that people have with it. And these are the most common ones by far I've seen of mistakes using fastai to predict. That being said, in a real world scenario, I can't really recommend you use fastai as an inference framework. Fastai to me is a training framework only, and the inference framework is there at the end to see how you did. But it should not go from training to production with fastai still attached. And so next, we're going to look at deploying without fastai. I've shown you sort of what, from a data perspective, that looks like, right? We've looked at removing the fastai transforms, but we're going to talk about removing it as a dependency entirely. Why deploy without fastai? Oh, there's a laundry list of reasons, but the main ones are A, fastai is not stable as a framework as a whole. And so as a result, dependency issue is single-handedly the biggest time and monetary sink when it comes to using this framework. For an example, firsthand experience, at my old job, I was tasked with taking a model and basically a pipeline that we had in production, and they wanted to bring it to fastai version 2. And fastai version 1 to 2 had zero backwards compatibility because Jeremy does not build libraries like that. And fastai v2 to v3 will also have this. And so if you're locked into fastai, when I had given them my time estimate, given all the inference experience I had of taking this thing in v1 to v2, which was being developed at the time, I had given them a budget. I had basically said about 2 weeks to take this whole pipeline, recreate it from scratch, and fastai v2, learn all the specific needs it needs, because they had a whole bunch of custom classes, custom transforms, and everything, because they were thoroughly integrated into the framework. And it was out of their budget. They couldn't afford that. And so it lives in fastai version 1. No one can touch the code because if you do, everything might break. And so from a code reliability perspective, it fails. From an API backwards compatibility, it fails. And from breaking changes that occur in any of the dependencies, it also fails. Because fastai does not do well with releasing versions. And what I mean by this is one of the most common issues people will have is they trained a model on fastai version, we'll substitute 2 for 1, 2.0.3 or 2.1.0. Let's say 2.1.0. And it works fine. But fastcore, what it relies on, introduced a breaking change. This happens very often. Fastai's dependency management is set to always inherit the highest fastcore version. And so even if you pin fastai and say, I'm only going to use fastai 2.1.0, that's not actually a solution. You have to pin fastcore. And if you pin fastcore, you then have to look at what fastcore does. It might inherit nbdev, so you have to go pin nbdev. You have to pin so many different libraries. And with most libraries and how typical software engineering releases work, you can expect that going from point 1 to point 2, everything will work the same. Nothing will break. And then, or like from 1.0.0 to 1.0.2, it's the same. And then 1.1 might have some breaking changes. fastai doesn't work off of this. There might be some breaking changes in some of that 1.0.0. And so it's not stable from that perspective. And the key with addressing libraries like this is you remove as much risk as you can, because having to hire someone to go through and take legacy code and update it in the software world, that is one of the most expensive things that companies do, is updating legacy software and maintaining legacy software. And so the less legacy you can have, which is by isolating dependencies, looking at risk management, and seeing and being comfortable with removing it, is one of the best ways you can be a good software engineer, have a good product, understand that this thing isn't going to magically break in 6 months for some reason. And I can't give that guarantee with fastai. It's come a lot. It's come a long way in things magically not breaking now in 6 months' time, but it still does. Things still happen. And so it's that is why the point of this course is to take you from taking Jeremy's course, where he showed that you can do these things, and understand, yes, you can. And Jeremy teaches you these things so you can, so that the barrier to entry is lowered. And what I want you to take from this and running with fastai after this is then saying, here's what he teaches. Here's why he teaches it. Here's why some of those things are flawed when it comes to the real world, and how do we mitigate that? And so this lesson is sort of the first step into that. I've been weaning you guys towards this throughout the course. From day one, well, really day two, we were sort of removing some of fastai. And all of that is going to come to fruition today. Because today is basically the last lesson. There's lesson 6 and lesson 7, but today's everything we've built upon of previous fastai knowledge and sort of understanding a little of how the framework works, and get you guys ready for after today. Go take a model deployment, go away with some of the good software practices from this, and be confident in your product of whatever you do, your space, your thing you're going to present to someone at a job for a project that you did, and be able to tell the story of why we're doing all of this. Because if it was up to me as a hiring manager and you said, okay, I took fastai, awesome. I know he got very good research skills, and I know he knows how to look at state-of-the-art things. That's great. That is a great green flag because he knows what's state-of-the-art. He knows how to deal with these problems, and he, goes through a very rigorous but thorough understanding of how to deal with state-of-the-art tech. If that's where it ends, that's immediately turned into a flaw. Because if their example just uses fastai end-to-end, I need to be able to know how he can take the lessons from this framework, he or she or them, and be able to apply it to my problem. Because I might not use fastai where I work for a variety of reasons. We could use PyTorch Lightning. We could just use PyTorch. But I want to make sure that getting someone from this point to using whatever we use is fast and quick, and they can be confident on their own 2 feet without the framework. And with this course, we're getting you there. You're not 100%, remove fastai, and I don't know, how to recreate the data loaders fully based on certain situations, but this is the start of getting a very critical skill set for being better than 99% of applicants that have taken the course and show that they know how to use fastai. I know that was a mild tangent off of a simple question of why deploy without fastai? Are there other reasons? But it's a great way to sort of talk about how you guys can talk about the skills that you learned and you've earned by taking this course. I'm happy, this is basically the end of where we're gonna talk about knowledge stuff to a certain extent. And so after this lesson, I'm actually going to give you guys course completion certificates, as long as you have shown me that you've made it to this point. From here, it's basically, I want to work with you guys on making sure you can advertise your skills with fastai and make sure that you're confident in what we've talked about here and being able to translate that into a resume, a CV, or a project. Should have waited until the very end of the lesson to have that, but I think it's a good introduction or interruption to have that keeps everyone's attention there. So I really do want you guys to be successful, and it kind of sucks that to be successful, no, it doesn't suck. To be successful in this field, never rely on a single framework. It's basically what I want you guys to take away from this. fastai is fantastic for getting things going, getting a model, training a model, and getting it ready. Any framework's going to be great for that. But then always be comfortable with, how's that framework work? How do things work under the hood? And how can I deal with very software engineering problems that the fastai course won't talk about? These are all software engineering concepts that, traditionally you'll learn through schooling that, to be frank, no one from fastai really knows, because most of fastai's graduates aren't software engineers. They took a year of Python, just like this course is designed to have a year of Python. And so what I'm trying to get you guys to do is have that year of Python, but your Python is better than everyone else's Python because you understand these ideas. And I mean, honestly, you could even get to a point where you remove even PyTorch. Alan made a great comment in the Discord about how there's a framework called Onyx. And if you go look at Fast Inference, a library I made a while ago, it converts to Onyx, and Onyx removes Python. Now you just have C++. It removes everything you possibly and it generally, how this sort of formulates is, as you peel back more layers, the more complex it gets, the more things you have to do. Sometimes there's a speed up, sometimes there's just dependency and reliability is a plus. And so all of these factors are things to take into account that I'll talk way more on in running. But these are like some of the important thoughts to have as you're approaching future projects, as you're approaching your current project maybe, and thinking about, how can we use this framework to our advantage while also mitigating the risks and the downsides to it. Because fastai is phenomenal if used well. Now, when I say deploying without fastai, what does this mean? Because, I talk about, let's remove fastai's dependency, let's remove magic. Really what this means is step 1, recreate the entire model without fastai from scratch. Now, this has to be done in that allows us to load the model weights back in. So we're not creating a model from scratch and then training it in fastai and exporting it. No, that's not what I'm going to show you. I'm going to show you how do we keep the model that we trained and then remove it from fastai fully afterwards. Now, in this case, we're minimally keeping Tim because Tim is stable, and Tim as a framework is how we get our model. This would be the same thing of if it wasn't a Tim model, it'd be a PyTorch model. And this is going to be using the model that we had a moment ago in deploying with fastai. Next, recreating the fastai transforms, which is something we've already looked at, before finally recreating the decoding step of predict, which we've also kind of done, but not fully. So this lesson specifically will not be using import star, because the point of this one is to quite literally let you copy, paste, and be on your way. So the first part we're going to bring in here is, well, really, this whole lesson here. We're not allowed to bring in fastai. We are not allowed to bring in fastcore. We're not allowed to bring in any patched material, nothing. It can only be used by the standard library, PyTorch, Torch Vision, and Pillow, and Tim. And that's it. So this is the limitation we're setting. We are completely removing fastai as a dependency after the fact. And so these are the imports we're going to wind up needing. From Tim, we just need create model to create the body, right? That create body that we looked at last time. We're going to pass in the model that was used in the previous lesson. We're not going to bring in pre-trained weights because we already have our own weights. And then we're going to cut off the head by using num classes equals 0 and set it to take in a 3-channel input. Now, of course, if you're using a PyTorch model instead, you'd extract the body in the same way that fastai's create body would work. And then we need to create the head. Now, to create the head here, it's a batch norm dropout linear ReLU batch norm dropout linear. When we're not using Vit and we say have mixed pooling, you would use fastai's double pooling layer, and maybe instead of an NN sequential, you'd have this be like an NN module that takes in first the pooling, the 2 separate poolings, averages them, and then has the rest of it. This is a very Tim example, but it can be done without Tim using fastai using a PyTorch model in how. So we load in the model, or we create our model first, right? Surrounded by an NN sequential, which is how fastai creates it, right? It's the body and the head. Now to make sure it works, we're first going to load in the weights. Now torch.load will take in this PTH file we made, and this is now a dictionary of the model weight and the optimizer state. And so each key is a layer, and then the value for that is basically the weights or the parameters. And the first thing you'll notice here, I believe the reason why this one doesn't raise an error is I set with opt equals false when I first exported. Otherwise, you'll have to do state model. The first issue that we'll see is we get this really weird missing keys in state dictionary where it talks about something 0 class token isn't there, 0 position embed, all of this confusing what's happening. And the reason for that is the state dictionary is basically how PyTorch and Python keeps track of these layers, right? And what winds up happening is in our state, so this is the model state dictionary, okay? The actual PyTorch model. You'll notice that its keys are like 0, some description, 0 position embed. And this is the layer group in this case, because it's created with fastai. 0 layer group layer. But in our saved dictionary, that's state, we have this extra model attribute here. And that's why we're getting this issue. So the first part is, if you notice this, take a look at the model and the state and try and see where the issue is. And there's ways that we can mitigate this. Now, the idea, this side note says, it's also this idea of transfer learning twice. So how do we take a model that I trained on, say, 500 classes that was pre-trained on ImageNet and bring that in customly to fine tune on? And it might have a completely different model architecture design as well, in terms of like how these things are named. And the way to mitigate this is through essentially two functions. So this first one, copy weight, takes in a layer name, a model parameter, and the dictionary. And it will load from the dictionary the weights for name in that parameter. Now, in this case, like there's nothing general about this per se. This is for this specific dictionary setup. So we can check if it starts with 0. And if it does, we know that means it's part of the body. So then we know that we need to add model dot to the name. Afterwards, we check and make sure that it exists in the state dictionary we're trying to load our weights in. We check we pull that parameter from the model, right? This is the saved layer weight for name. And then we make sure that its shape is the same shape as what we're trying to load in. So this helps with issues of like fastai's layers will be named the exact same, say in the head, even though it might have a different shape. You know, it's got 37 classes instead of 5,000 or whatever. And so this will check if that is the same. And if it is, copy is in place and will copy these parameters and set them to the parameters of this layer. And then I have a few else statements that basically say, okay, if this fails, it's because there was a shape mismatch. And here it's because it wasn't in the dictionary. And this is the core PyTorch way that you deal with loading. So when we do torch.load, it's essentially doing this. It's doing this, grab the layer from the state dict and then copy that parameter in. This is what it's kind of, there's a bit more convoluted to it, but under the hood, this is what it's doing. And then what this returns is it modifies the parameters, right? So this is the parameters from our state dict of the model versus the state dict trying to load. But we still need to apply that state dict to the input model. And so that's what this does. So it takes in a model, some weights that we want to load in, and a function to apply those weights. So here it's our copy weight. It will grab the state dictionary for every parameter and basically literally every parameter in the state dictionary. Go ahead and try loading all the weights before finally, in place, load those weights into our input model. And because this is done in place and it's by reference, we don't actually need to return anything. The model that we have loaded in will have this state dictionary updated for us. So that's why there's no return input model. It's really actually not needed. And so if we take apply weights, send in the existing model, this state that we loaded in a moment ago, and our copy weight function, no errors are introduced. And so this is, for a time, for a very long time, this general pipeline and thought process is probably single-handedly one of my most bookmarked and referenced and gone to forum posts, which I'll, like, if we do fastai transfer learning twice, this is a discussion post about it. And as we go down, you know, you'll find that eventually it should get to a point. No, this is not it. I'm sorry. Let's see if we can find it real quick. Welcome to how I search for things. So if we do transfer learning twice, let's see. I guess it isn't here. So you see the first part where they talk about changing the model. And then somewhere, I'm doing this live because of course I did not check this before we came. Somewhere in here should be a function. Again, apologies, we're doing this live. I sort of just now decided that we would look at this. Maybe it is this. I could have sworn there was a better way to do this. Uh-oh. In any case, I will find this thread because it should be somewhere in my bookmarks. Again, sorry for the like unplanned going down and going through this path. I would have preferred to have this bookmarked beforehand, but I guess not. There we go. Oh my days. This was fun. I'm throwing this in the Discord. It'll be in the lesson notebook. Have fun. But basically, this idea that we're doing is based off this single forum post, which needs way more likes, in my opinion. Way, way more likes. Because this little code snippet here is what probably single-handedly opened up the idea of removing fastai from things. But this code snippet is the key towards doing this transfer learning twice idea. And this idea of let's bring in these new weights that don't align with this current model and make it, because I know that it's the same thing. So now let's move on to the item transforms, which this one was single-handedly the hardest part in prepping this for you guys. And I'll sort of talk about why. But if we remember, basically the old model had random resized crop, to tensor, int to float tensor, aug transforms, and normalize. And you notice that this time we're not skimping out on the batch transforms. I'm showing you a fully fleshed out what fastai teaches as the good way to do data augmentation, because it is. Now, if we think about these transforms though, so random resized crop, which we've seen already, on the validation set, we'll use crop pad essentially instead. Flip and brightness, which come from aug transforms, aren't applied in the validation set. But, and this is very important, because of this size here, it adds in a transform called random resized crop GPU, which this one, as you'll see, is not the same as doing center crop or crop pad. Now, you'll notice that I'm bringing in fastai imports here. This is strictly for us to ensure that fastai versus our recreated methods are the exact same. And NumPy is here just so that way we can do assert statements easily for checking. Now, the first thing when you want to do a test like this, where you want to try and recreate something, is keep it simple, stupid. So we're going to use one input and try and adapt that one input at every stage. So we'll get a path, download our data, get a single file name, and we're going to use this Siamese. Next, we're going to open it in the respective APIs. So respective meaning how fastai opens it versus how Pillow opens it. And so we'll use PILimage open and PILimage create. And we'll use this first assert statement to basically ensure that these are equivalent. Now, they were. These are the exact same because it just opens in Pillow, and NumPy array converts these into an array, and we can check those. So these are now exactly the same. Next, we're going to do crop pad, which crop pad should be, if you're thinking about it, the same thing as center cropping, because that's what we do. We center crop the image. So if we use torch vision and center crop, it is not the same. And basically, to recreate how it does center crop, it takes 4 points or 2 points, the top and the left, and the height and the width of the end image, and crops it to this box that's created. Now, in the code and explanation tab, I show in pretty engorging detail how this works. For the sake of the lesson video, understand this is what we're doing. And so this is the first part. This takes care of the crop, but pad is another step that we're missing, right? So how do we deal with pad? Pad is going to look very similar to what we just did. Top left, and then take the padding for the top left, perform basically what that padding needs to be, and call the pad function. And by default, fastai uses a constant padding mode. And again, there's a thorough explanation as to what each line does. I highly recommend studying these because it helps rip away some of how fastai's transforms work without looking at the code. Because this step here took me about an hour to recreate by going through fastai's code, examining it, checking, okay, this is what that word means, this is what that word means, and converting into something that is readable to you that fastai's code makes horrendous to read. Which, to reiterate that statement, remember that white space matters, lines of code matter, variable naming matters, and white space matters. So when writing code everywhere, please make sure to not try and be lazy with keeping number of keystrokes small. Be explicit. Your future self will like you. So if we test this on a size and we do a crop to a size and then pad to that size, and we check it, what we find is this successfully recreated the fastai image. And it took, if you get down to it, 3, 4, 5, 6, if we were caring about lines of code, 7, 8, 9, 10, 11, 12. 12 lines of code to recreate what fastai delegates to. That's not bad. Now, here's where the fun begins. That was CPU. Now, to recreate that on the GPU, it takes a bit more because now we're dealing with matrix calculations and trying to do the same thing, but without any padding or whatnot. It's very different in how this one specifically, if you don't understand, that is okay. There is a code and explanation tab here. However, if this doesn't make sense to you, that's okay. The point of this one specifically is not to have you understand it. This GPU crop is strictly so you can hit copy, paste, and use it. Because I personally don't think you should study this code for GPU transforms like this. You just shouldn't. In this case, the transform should be done on the CPU because it's simpler, uses more things in the box, and the speed up isn't that important when we're dealing with production. So basically, after all of this, we again do a check. So here when I'm testing, it's going to be those assert statements again. Well, really, it's torch all close, which I'll talk about that in a moment. But in order to test this and sort of how I do this A/B test, we take our 2-tensor fastai, int to float tensor fastai, and random resize crop fastai. And then I'm going to take the torch vision augmentations, which is just 2-tensor, because remember, it will automatically do int to float tensor for us. And we're not normalizing here. We're just trying to recreate random resize crop GPU. So we'll crop it and then apply our transforms. We do unsqueeze 0, turn it into a batch, and then split in idx equals 1 here on this transform call so that it knows to act like it's the validation set. And we do the same thing using our torch vision transform. So turn it into a batch, crop it into 224 at the end. And of course, I'm teaching you this, but to test this, instead of an assert, because we're dealing with floats, you now use all close. And we can see that the output from fastai's transforms recreate the torch vision transforms that we used. So now that we have basically everything, the last step is normalizing. And with normalizing, we can just use torch vision for that because it's normalize, and fastai does nothing special in normalization. It is 1-to-1. Because you can't really normalize different ways with PyTorch. That's accepted. You can, but it's not done. So, we can apply this all at once, check it, and now we can deploy it, right? So we can deploy based on this snippet without using fastai. And below here, I have a very quick copy paste for you of the code for you to look at and reference, and particularly copy paste, because as noted here, no one has done this. No one has taken the fastai transforms and made them readable and extract the magic. And so this is the only real reference of this that exists. Now it exists in the GitHub, I believe. I was debating if I wanted to even include this or not, but it's there. And please, because it is probably one of the single most important code snippets I've ever made in my life. And that's not even me trying to toot my own horn. It's just, this is one of the most common questions that people want and need due to the deployment issues that I mentioned earlier. So we'll go ahead and take a 10-minute and feel free to drop in questions you have over deploying without fastai. And then afterwards, live together, we will go through deploying and creating a basically Gradio app using these two exported models we made. Why did we go through the effort of recreating the fastai transforms? Right? Why did we do this in the first place? And the reason is our model was trained specifically on inference, the inference, to have the images be prepared in a particular way. This includes this whole padding, cropping, and so forth. And so if we don't recreate exactly what it did, like say we use just the crop pad that PyTorch had and we normalize and we're on our way, our predictions will be different than what, say, we did .predict with. And so the data wasn't prepared in the same way that we trained on, which is not what you want. You want to be able to have your data look and be the exact same that it was trained to have the data look and see like. That's why we do data augmentation and why we have validation transforms that look a specific way. That doesn't mean limitate by size, because deploying with a bigger inference size is still valid. But it means that when you're deploying, you still need the expectation the model has for the image to be the same. Another way to kind of think about that is, say you spend, an hour or so getting prescription glasses, and your prescription is perfect, right? So you trained with the doctor to have a particular prescription for your lenses. And then when you get the glasses, if you don't have the exact prescription the same, your vision is still going to be a little blurry. It won't be wrong. It won't be horribly wrong, depending on how bad it is, but it'll be off and still different. And so that's why it was important that we make sure to remove the fastai transforms and make sure that they're different in that sense. So there's a difference between torch visions, random resize, and fastai. Yes, that is why at every step of the section here, I do a comparison to check this. So when we did crop pad versus their center crop, it's different. And then when we use their random resized crop, if you check it, it will be different. This is not the same. That's why this went through. I probably should have done random resized crop here as a comparison instead of assuming, because that's a very good point. But yes, it is in how it works, which is why we went through and did this. That is a very, very, very good question, because I did not really... I'm much happier with that explanation as to why we do all of this. And generally, when you think about how fastai does literally anything, always assume it does something different. It does something weird, it does something funky, and nothing will quite recreate it exactly. Because 9 times out of 10, that is true. And then test, like we've done here, to make sure of that. This is especially true for the data API. The like CNN learner and stuff, not as much. Like there's a few custom layers that I mentioned earlier. That code is pretty easy to read and navigate through and deal with. It's the other part, it's the data API. Why is random resized crop needed? Specifically, it's because with how fastai uses random resized crop GPU, because the image needs to be the same size when training either on validation or the training dataset, this is one of the exceptions to the augmentations that aren't done only during training. Because it's not something that modifies the look of the image, it's something that modifies the overall. So on the CPU or on the validation set, it is equivalent to running crop pad in your head. Like the code obviously looks very different, but it is essentially the same thing. It is center cropping to 224 on the validation dataset. Otherwise, we could just completely ignore this, only do, crop fastai and be, but that is not the case. And that's why this split IDX equals 1 is very important here for you to see. Because if you look, split IDX equals 1 is the validation, right? This is the validation data set. And if we didn't resize 224, this would be false. This torch all close would not be true, because the result from fastai would be still 460 or whatever, and the result from torch vision would be wrong because it's 224 by 224. And the general way to tell that when you're looking through the fastai transforms is if it's a rand transform that has a split IDX of none. Let me show you what I mean here. So if we go pull up the fastai, that was not what I wanted. So if we pull up the fastai source code here, this is a very good topic for us to hammer in on. The transform lesson will talk about this more, but it's a good side tangent for us to have. So if we look at the rand transform source code here, this is what random crop and whatnot use. You'll notice that there's this before call thing that says do is either if the probability is 1 or if the probability is something to apply it, right? So this is the check of does it run only on the validation or the training, or really not even that. It's if it's applied. And then what's important here is split IDX of 0. And so when we run this before call basically says, okay, so by default, the split IDX for this transform is 0. So it'll always be 0. But if it's not, if it's, say, something like none, I need a way to check that based on the current split index. Now, keep that in the back of your head, and let's go look at random resized crop GPU. Now here, when we're looking at this, the split IDX is none. And so when you're looking at these transforms, if you look for a split IDX of none, that means that it's special. It is a transform that has behavior that occurs on both the training and validation. And on top of that, remember that self.do that determined if a second ago if the probability was something it applies on? It is always set to do something. What happens here is there's specific behavior of if the split IDX is 1 or not. This is that center cropping. That's why there's not all of this math random stuff that I recreated, because the snippet I showed you is strictly for inference. So it has just this split IDX portion. If your input data is preprocessed to the right size, you won't need to crop at inference time. Yes and no again. It should be cropped in the same way. So, like if your inference, well, let's go with this. You're right. Yes, you're correct. The better way in my head to explain that to you guys that makes sense to me is if your input data is preprocessed outside of fastai, right? Similar to the segmentation example I showed last week where it was everything came as a size 224 already. We didn't need to do any cropping. Then you don't need to do cropping at inference, nor do you need to do cropping at training. And so all of this can be avoided. It just depends on if you want to perform that augmentation beforehand and store all those files on-prem or do them, as you bring them in, versus having them done with fastai. Because if you do it that way, then you can use, Torch Vision, Scrop Pad, and be on your way. That is a very, very good point, Alan. Yes. All right. So these are all very, very good questions. Excellent questions, guys. I'm loving this. So now let's talk about, Gradio is a library by Gradio, which was then bought by Hugging Face, to basically write a super simplistic interface for you to implement deployed inferences. So, in this case, you have an example with speech recognition where you write a function that takes an input, you create this interface that takes in a function, something for an input, say my output needs to be blah, and do this launch. And so in a very few lines of very readable code, you can set it up, do hosting in spaces. It's very easy to get the ball rolling and can mimic the real world. And what I mean by this is you can take this and deploy it as an API directly. And so you can use it through, say, GET requests, no Python involved, shoot it some bytes and have it return what you need. There's no special wrapping you need to do in confusing parts. That's one reason why Gradio is very, very well. Very, very good for this project. There's a few other Gradio-like options, such as Streamlit. This one is biased because I work for Hugging Face, but also I work for Hugging Face because I like the tech they use. So it's not a blind endorsement. You can be upset at that or choose not to be, and that's all right. I won't blame you for that. But the same idea can be done with Streamlit instead if you wanted. Now, for this problem, what I've done over here, you can't see this because I need to switch the windows. 1 second. There we go. All right. So what I have done here is I've created basically a little lesson 5 folder that has the pickle file from that load learner and the PTH file from the saved weights. And this first app is just going to use load learner and be on our way. So the first thing we're going to do is say from fastai.vision.all, or not even vision, from fastai.learner, import load learner. And we're going to attempt and see how well, I'm going to change this to fastai actually, if I can. Looks like it will not let me. That's okay. I'm going to go ahead and get into here. You're going to see Colab being used, or Copilot. Sometimes it's good, sometimes it's bad. Like here it's giving me a fastai version 1. So bear that in mind. But we're going to bring in 2 imports. We're going to bring from fastai.learner, import load learner, and from fastai.vision, import PIL image. Now, in this case, it's because we're going to create whatever we get into a PIL image and then send it to fastai, because as we saw earlier, you can do that just fine, and the PIL image creation will do basically nothing. And then the other thing we're going to bring in is a way for us to use Gradio, which is import Gradio as gr. And do tell me if the text is a bit small. Actually, I could probably blow that up a little bit. And now that we've seen those files, yeah, that looks a bit better. I want to, okay. Well, you can see that. And this code will be available after the lesson. But I really wanted this to be a let's code live. You can see how I do live and be on our way. So this Gradio is super important. So the first thing we're going to do is, as Copilot suggests, load them, which I'll call this just learn, equals load learner. And we're going to use our model that we have. So here it's not export.pkl, it's exported fastai.pkl, or pickle. Next, we're going to get the labels, just as a quick way for us to look at it. Now, this is highly based on a open source version hosted in Hugging Face. I'll post the space in the chat, but it is by Kaisiba, or Kai Ingri Espinin. And it's a really simplistic interface to do predict for image classification. I like it a lot, so that's why I'm using it for this course. We're going to do get the labels so we can decode it without needing to do... Actually, I don't like that component. We're going to get rid of labels. We're just going to use the output from predict. And then we're going to basically write a function that classifies the input. This is all correct. And then we're just going to return pred. So basically what this is going to do is take an image or an input of whatever we upload to the space, convert it into a PIL image, run predict, return the class. Because this is all I want to do, right? Now, this is basically all the fastai part done. And now we're going to create a Gradio interface. As Copilot suggests, this is actually doing pretty good. I'll be a bit more explicit. So we'll say functions classify input. Our inputs, we're going to say it needs to be a image. And because, I mean, we don't have to specify a shape, but we can have Gradio pre-crop it for us, which is nice. And then we're going to say its output is text. And that text is basically just going to be the class. And then for the title, yeah, that's pretty good. We'll call it fastai classifier. Description, also good. And then to launch it, we say .launch. And let me make sure. I need to install Gradio here real quick. But basically, we bring in fastai, bring in the learner, and load everything in. Now, from a deployment setting, another thing we should do is specify a requirements.txt file, because this is, again, being trained on fastai. And so we're going to say pip show Gradio. I'm going to specify Gradio equals, what do we have here? 3.18.0, fastai equals, and fastcore equals. Because this does have fastai being done. So we'll do pip show fastai, and so we'll say 2.7.10. We'll look at fastcore, and this is 1.5.28. So that way we have all the dependencies of fastai marked. This also requires torch, but because it's using fastai, that should be fine. Shouldn't we need to specify CPU or a GPU? For the sake of clarity, yes. I'll say CPU equals true. Eventually, I'll have this deployed in a space as well, similar to the app that's shown there. Quite literally, it's a 1-to-1. I only have a CPU space. I don't have a GPU space. So that's why it's CPU only. But yes, say if I wanted to run this on my local GPU, which we will, I'll set its CPU equals false. Excellent point. And now that we've sort of declared our requirements, we could get even further with this. You could specify the pillow version, you could specify the torch version, which actually we should do. I do like that idea. Pip show, actually it should be pillow. So we'll do pillow equal 99.4.0, and then torch and torch vision. I spelled vision wrong. Torch equals 13.1, and then torch vision 0.14.1. And so this is all of our dependencies the project will fully need. Pinned. And pinned means only this version. We'll go ahead and clean up this a bit. This is just me wanting to make sure this code looks nice. That looks fine. And now we can run Python app.py. And this will, oh, there we go. Messed up the vision import there. Again, doing it live. Occasionally forget things. Don't forget we also have Tim. So I need to do pip install Tim, because we removed fastai as a dependency, but not Tim. That's going to be 0.6.12. And you will see that it basically opened up saying, hey, we're running at this URL. So if we open it and open up OBS to basically adjust this, you can see we have our fastai classifier here. That takes in an input. So if I go to images, let's see here, pictures. I know you can't see the pictures. I'm going to do something obnoxious because I don't really have a picture of a cat or a dog. So it is a meme of "It is Wednesday, my dudes." I can hit submit and it will run predictions and think that it's an Egyptian meow. And that's it. You know, it was all of, when you boil down to it, 4, maybe 5 lines of code if you don't care about white space. If you do, then it was, 20. And this is a fully deployed now fastai model where we can upload something and generate the output. So this is the fastai native version. So I'll go ahead and rename this app fastai. And I don't want to run file renaming participants. Now let's create an app fastai. Now we can start with the fastai template before moving on to other things. So give me just a moment. I'm going to copy the code that we have from here. So I'm going to create a new file, and we're just going to call this transform.py. And it's going to hold all of the transform code that we made a moment ago. So if I go down to the code down here, copy. So we're going to have this. We're going to have crop. We're going to have pad. And I know you can't see what I'm doing on the other screen. And we're going to have GPU crop. And here, then what I need to do is basically add a init file so that Python won't yell at us when we do from that should be transform import, and we want all of our options. So really it should, yeah. Transform import crop. What do we have? Pad, crop, and GPU crop. Crop, pad, GPU crop. Now, sadly, it's not liking where we're doing things off of, so there might be some live debugging here. But this is the first step, right? So we need to create our crop. Then we need to load the model in, which for that, we're going to import torch. So we're going to do import torch. And here, we're going to recreate what we did earlier. So if we create a new file, and we'll call this one model.py, I'm basically bringing in everything we had earlier, and then we're going to create a function called getModel that first will run the create model code, create the head, and I'm literally just copying and pasting, create the model, and return it. So then we can do, we'll go ahead and throw the copy weight in here as well. So we'll throw copy weight and applied weight in here. Yeah, I don't like that it's not picking up things defined in Pylance, but that's okay. So then we can do from.model import get model and apply weights. And to load the model in, we're basically just going to do sort of what we did before. So we're going to say model equals get model, and then apply weights. And really, we also need to do state equals torch.load. And this should be exported model.pickle. And when you're doing torch load, this is how fastai does that whole load the model and force it on the CPU. This map location, I'm just going to ignore that. So we'll get the model, get state, and right now it's on the CPU. And then we'll do apply weights, model, state, and I don't think apply weights needed anything else. Oh, yeah, so it does need copy weight. Okay, so we'll bring in copy weight. That now loads the state. We can then turn it to the GPU by doing model.CUDA. And now we have our model. So this is what I sort of showed there is creating a Python project from our code. And I know some of you might be surprised right now that I'm choosing not to do this with any. It's faster and easier to do it this way and better over time, in my opinion, especially with something like this, where we want it to be deployed at some point. Because the amount of friction that occurs with Jupyter Notebooks when it comes to the rest of the world is very high. So now we need to do classify image, which for this, that involves us doing from PIL import image. So we can do input equals image dot input. That has now done the same thing. And then we can say transformed input equals, and then we can do what we did a second ago, which is basically doing, how do we do this? We did, sorry, I have the other screen up because I can't remember off the top of my head the direct order this needs to be in. So it's going to be pad crop input 224, 224, and then transformed input equals GPU crop that to, and this one's not 220, actually this one is 224 by 220. The previous one was 460 by 460. So this gets our transformed input. We also need to do a unsqueeze somewhere in here, I'm pretty sure. Yes, it's to be unsqueeze at 0, followed then finally by normalize. So we'll say from torch vision forms import to tensor normalize. Yeah, because it doesn't need to do tensor. Then we can say norm equals normalize. It's already going to have this for me to quickly fill in. And then we can normalize our input. And that should be exactly the same. Not quite. We also do need to tensor. So we'll say norm equals that, to tensor equals to tensor. And this was done before the GPU crop. So that's going to be unsqueeze 0. There we go. This is the full version of it, condensed. So now we do model.eval with torch.nograd, and there's our predictions. Now, of course, this isn't our decoded predictions, right? So for that, we need to go ahead and decode the data. So we're going to do pred equals torch argmax. And then for our vocab, for here, don't be like me and get the vocab beforehand from the model. But for the sake of quickness, only to get the vocab, since we're doing this live and my Jupyter environment isn't the most handy. Actually, no, there's a way we can do this. We can do dot vocab, except then this needs to be boop and boop. Hopefully that works. Oh, dot dls dot vocab. Nice. All right, let's save this. Then we'll say equals this, and I'll clear this up for you. And this is just to make sure we can decode our predictions fully in the same way fastai would normally do for someone. So we have a lot of classes here. I'm just using the enter key so it's a bit more readable. All right, so we have our vocab. And now we just need to do return vocab at pred. And now, hypothetically, this should do the exact same thing. So if we do Python app no fastai, and it is going to give me trouble about this. So let's see if that helps. Nice. Okay. We're here. And again, I will share these with everyone. Let's see. It's saying something about, oh, yes, because that shouldn't be PKL, that should be PTH. All right. Live debugging is always fun, but one reason I'm doing this specifically On one hand, I could defend myself and say, this is laziness. But really, it's because one thing you guys have told me is you love watching me do live debugging. And so that's kind of why this section I want it to be a lab where you sort of see how I would go about this. I knew about Gradio and I did a like deployment of this earlier, but I sort of wanted to give you a raw experience as well, where it was planned, but I fully understood we were going to hit some headaches. So we have our fastai classifier, which really, this is just my own nonsense. Not quickly editing it so that way it's a bit better there. An example not using fastai and Gradio. Upload my dudes. And what did we get? We got an issue somewhere over here. So I did something wrong. Hang on. I see what's wrong here. So you guys can understand what was wrong here. I currently have it only as window. But basically, when we do Gradio inputs image, it will return a NumPy array. So we need to make sure that instead of doing from image.open, it needs to be image from array. So if we refresh this, do this, and do that. Oh, fascinating. Let's see here. I'll switch over. And again, sorry, this has taken like a left turn. Basically, the error I'm getting, oh, that's weird that it's not letting me show the VS Code. Maybe I need to, there we go. Okay. So basically some of the issues we're dealing with, and this is good to show as well, is when I built this thing, I was not very careful how I was keeping out for fastai patches. I was looking at the source code and assuming that, it'd be working one to one. And one of the things you'll notice here is we're getting this error that's saying attribute error shape. And this is in one of the transforms I wrote in line 22. So it's this part. And this is because pillow doesn't work with shape. Pillow works off of size, and size is the inverse of shape. So what this means is everywhere we have shape at a bracket, they need to be reversed. So this needs to be 2, this needs to be 1, this needs to be 2, this needs to be 1, again 2 and 1, and then on top of that, instead of shape, that's fine. 1, 2, this also then needs to be reversed, I believe. No, those need to be the same. And actually that needs to be the same as well. That's fine. On top of shape, they need to be size. This is what I also mean when I say dealing with fastai code can have issues. Its use of monkey patching leads to issues like what we just got. All right, so let's see if that fixed most of our stuff. You'll notice that there's this part in here. Interesting. So our weights aren't working. Something with how I'm loading the model doesn't work right. But last thing from torch. Where's F defined? There we go.